Okay, we're going to continue on here. Chapter 2 we're in. And last time we were talking about really waves. We were talking about how to calculate energy and wavelength. So we have some important equations. C is equal to the wavelength times the frequency. Again, remember C is a constant. It's the speed of light. It is 3 times 10 to the 8 meters per second. That means, though, because of these units, when you do have the wavelength, you do need to make sure it is in meters when you're using this equation so that everything cancels out correctly. Frequency is reciprocal seconds. Also, a reminder that we talked about that reciprocal seconds is the same thing as a hertz. So that is also a very common unit of frequency. We saw that we could calculate the energy of a photon of light that's coming off as electrons, for example, transition from one energy level to the next. The energy is equal to h times the frequency. This is Planck's constant. And that is your 6.63 times 10 to the minus 34 joules times seconds. We also have, again, our frequency here, which again is reciprocal seconds. Unit wise, when the reciprocal seconds and the joules time seconds cancel, that will typically give you your energy value in joules. We could also relate both of these together as the frequency is equal to c divided by the wavelength, which means we can incorporate that in. E is equal to hc over the wavelength. Both of these being the same constants that we talked about, which means, again, essentially, if you do know the wavelength, you can calculate the energy associated with that photon of light. Again, here, the wavelength does need to be in meters for everything to properly cancel out. But again, if you know the wavelength or you know the frequency, that will allow you to calculate the energy associated with that photon of light. We talked about sort of the idea of Bohr model of the atom, which is more that planetary model of the atom. And again, as electrons transition from one orbit to the next, this sort of idea of quantized energy, which again means, as we talked about, that essentially they will either gain or lose enough energy to fully transition from one energy level to the next. They won't be in between or anything like that. Um, and what that gives you when you have sort of that quantized energy, as we'll see today in lab, as we talked about and we saw earlier, it gives you, in terms of as these guys are transitioning, a more line spectrum where we see lines of distinct wavelengths coming out, and obviously distinct colors. And that's different than sort of a continuous spectrum that we talked about as well. Like, for example, the sun will sort of give off where basically all the colors will sort of come out at once, all the wavelengths will come out. And this was sort of that analogy we use of sort of staircases, which is quantized energy, where you'll either be on one step or the next, versus, say, if you're walking up a ramp where obviously you could just stop anywhere you like along the way. You don't need to get enough energy to go from one step to the next. Now, as these electrons are transitioning, as we talked about as well, it is a endothermic process, right? When the atom gains enough energy to excite that electron up to a higher energy level. And then obviously, as it relaxes back down, it will give off that energy in the form of a photon of light. That is a exothermic sort of process there for the atom as the energy is being released to allow those electrons to transfer back down. Now, we saw at the very end that we can calculate the change in energy as an electron transitions from one energy level to the next by using something like this equation here. If I don't run into things here. And this is, again, sometimes referred to as Rydberg's constant, 1 over the initial sort of energy level, or sorry, final energy level minus the initial energy level there, and that will calculate it. Now, as we talked about when we use this equation, there it is right here. So again, when we use this equation, it's important that when you do calculate the change in energy, if it's negative or positive, obviously that you should keep it. When we do end up with a negative value for energy, that again will tell us that we're looking at an exothermic type process occurring. When you have a positive value, again, that will be an endothermic. Now, if you use this equation, or if you calculate energy just in general, and you do end up with a negative value for energy, once again, you should keep that negative value. But if you're going to then perhaps use that equation or that number in one of these sort of calculations we're talking about here, which, by the way, you can set this equal to h times the frequency, or hc over the wavelength. We're going to use that energy value to either calculate the frequency or use it to calculate the energy or the wavelength. Both frequency and wavelength should be a positive value. So if you're going to use that energy value in those calculations to do wavelength or frequency, all you have to do is basically just drop the negative sign, make it a positive number, and then obviously you'll end up with a positive number for your wavelength or frequency. The idea behind that is the conservation of energy, which means, right, if something loses a certain amount of energy, something will gain the same amount of energy. So the energy value is going to be the same regardless of the sign. And that's why we could just sort of drop it, if you will, to figure out the frequency and the wavelength. So frequency wavelength should be positive. If you calculate energy, can be positive or negative number. And again, you should leave, obviously, it in that sense. Any questions on any of that there? All right, so we left off with an example that you were supposed to have completed. So let's take a look through this one and grab the calculator here. There we go. And on this one, we're going to calculate pretty much everything. So we're going to calculate the change in energy. We're also going to calculate the wavelength and the frequency for each of these transitions of electrons from different energy levels. Remember that n equals 1 is the ground state, and that is the closest to the nucleus. It's the most stable. N equals 2 through 7, for example, are what are referred to again as excited states, and those are higher in energy, lower in energy. So as we do these transitions of n equals 5 to 2 and 4 to 2 and 3 to 2, we're going to basically try to figure out what is going on here. So we'll start with the first one, and we'll take a look at it here. So n equals 5 to n equals 2. So obviously that's really the only piece of information sort of given to us. So we are going to basically start with the transition and the different energy levels and do our calculation there. So this is going to give us the change in energy is equal to minus 2.18 times 10 to the minus 18 joules, 1 over n squared final minus 1 over n squared initial. Again, this would obviously be our initial. This would be our final. So that will give us minus 2.18 times 10 to the minus 18 joules, 1 over final squared. So that is 2 squared, which is 4. Not equals, but minus 1 over 5 squared, which is 25 in that case. So I'm going to do what's in the parentheses first. So we're going to do a little 1 divided by 4 minus 1 divided by 25. We're then going to times it by 2.18 to the minus 18. And that is going to get us here a negative 4.58 times 10 to the minus 19 joules. Here our energy is negative, and that does make sense because in this case, our electron is starting up on the 5th energy level and dropping down to the 2nd. The only way to do that, right, is to give energy off, and that should be exothermic and a negative number, right? If our electron was heading in the opposite direction, which means it was going from the 2nd energy level to the 5th, the only difference is the sign would be positive. You get the same number, so you would still get the, whatever it is there, 4.58 times 10 to the minus 19 joules, but it would be a positive number because the electron would need to gain that energy to jump up to the 5th energy level. So regardless of which way you're going, the number will be the same. It's really the sign that's really important for the energy aspect of it. And again, that's why we want to keep the negative. If you do get a negative, or obviously if it's positive, keep it positive. Now, with that, we can really do a couple things. Depends really which way you want to kind of calculate or what you want to calculate first. Remember that E is equal to H times the frequency, which means, frankly, we could calculate the frequency by solving this as H is Planck's constant. So this is one approach. Frequency in this case would be our energy divided by our Planck's constant. And that would give us, again, here, I'm going to turn my energy into a positive number so I do not end up with, obviously, a negative frequency. Planck's constant is that 6.63 times 10 to the minus 34 joules times seconds. The joules will cancel each other out when you divide, and you will end up with here a frequency of 6.90 times 10 to the 14. These are, again, going to be reciprocal seconds in terms of the units here. Now, again, once you have that, you actually still have two options of how you want to solve it. You could roll back to our original equation, C is equal to the wavelength times the frequency. And in this case, we could solve for the wavelength, which would be C divided by the frequency. And that would give us 3 times 10 to the 8 meters per second, which is our speed of light and a constant value. We could put our frequency in there that we just calculated. Here, the seconds will cancel out when you divide. Remember, as we talked about as well, definitely want to make sure that you use your exponent button. Yeah. Yes.
When I divided 4.58 by 6.63, I got 6.91. I found it for second. Because it's 6.9.
Let me take a look. Yeah, you might have got it. You might have got the same question or different question. Yeah, you might have got that. I actually used the whole number in my calculator rather than the rounded number, and that's probably the difference. On my calculator, it was 6.904 times 10 to the 14. Either one would be fine. It's just I just kind of continue as the whole number. Yeah. Yeah. Yeah, so you want to make it positive. Again, the idea is you can't have really a negative wavelength or frequency. So if you do end up with a negative value for energy, just basically make it positive, just use the number. Yeah. But again, as we talked about, if you're given the answer for energy, you do need to leave it negative because again, yeah.
And then would you say, like for chapters 1, 2, would there be practice problems like on the textbook that you can find all of the math or the logic?
Yeah, I would assume you could do the homework and any other problems in there would work. And I think there's a couple of worksheets and stuff up there, maybe some practice type up on a canvas and stuff like that. Okay. Yep. All right. So if we punch this in, we are looking at, in terms of our wavelength, 4.34 times 10 to the minus 7 meters. And here we're going to calculate this in nanometers, perhaps. And I remember that nano is 10 to the minus 9. If you don't know that, you definitely after today's lab. So 1 nanometer, by the way, then would equal 10 to the minus 9 meters. So again, that is the proper way to use that. And you can then do that, obviously, 1 nanometer, 10 to the minus 9 meters. That again is basically 1 times 10 to the minus 9. So that's basically what you're going to divide it by, making sure to use your exponent button, ending up with a 434 nanometers as our wavelength there. And in that case, looking maybe something like blue, maybe in terms of our wavelength there. Now, as I mentioned before, I did go into this equation here to get to the wavelength, but you could also use, because we did have the energy, hc divided by the wavelength, and solve for the wavelength for hc divided by E. So you could also have one into that equation as well, should give you, again, the same answer as you go through it. Any questions on that one there? All right, then let's take a look at the next one there. So again, we're somewhere in the bluish range, I think. The next one is a 4-to-2 transition. So we'll do the same thing. So B is 4-to-2. So once again, we'll start with our change in energy. We're going to do 1 over our final, which again is basically 1 over 2 squared, which is 4, minus 1 over our initial, which is 1 over 4 squared. That's 16. So remember, you are squaring it. You're not multiplying by 2. So make sure, again, 4 squared there will get you 16. And in this case here, we're going to punch our numbers in. So 1 divided by 4, the minus 1 divided by 16. We're going to times it by 2.18 to the minus 18. And it looks like we will end up with a negative 4.09, we'll call it, times 10 to the minus 19 joules in this case. Once again, this is a negative value exothermic. As the electron is dropping down in energy levels, it will be giving off that energy. Once again, we can roll kind of whichever way you want. So to mix it up, just to show you, you could kind of do a different one if you want to do it this way instead. We can use this to get to our wavelength. So if we do that, our wavelength would equal hc over E. Each of those on top are our constant, so that's our Planck's constant, our speed of light, divided by our energy. Once again, we're just going to make it positive so we do not end up with any type of negative. Joules will cancel, seconds will cancel, and that's going to hit us meters as the answer out of this move here. So that'll be 6.63 to the minus 34 times 3 to the 8, a little dividing by 4.09 to the minus 19. That's going to get us 4.86 times 10 to the minus 7 meters. Once again, we're going to put it into nanometers since we're looking at colors, I think, here. So that'll give us 10 to the minus 9 meters is 1 nanometer. And we'll divide that by to the minus 9. So we're going to end up with a 486 nanometers, maybe greenish color. Now that we did that, again, you still have 2 options. You could, to get the frequency, you could use E is equal to H times the frequency, or you could go with our wavelength times our frequency as well. Again, whichever one you want to roll with here should give you the same answer. I'll go with the frequency is speed of light divided by the wavelength. That's going to be 3 times 10 to the 8 meters per second. The important thing here is units. So although I did solve for nanometers for my wavelength, I do need to use the meters version of it here so that the units properly cancel. And that will give us 4.86 times 10 to the minus 7 meters. Again, using the meters ones will allow it to properly cancel. And a little dividing action, maybe. That's not the right one. Let's try that one here. We will end up with a 6.17 times 10 to the 14 reciprocal seconds, which is our frequency in this particular case. Any questions on that? So again, there are multiple ways you can kind of get to the answers depending on sort of which path you want to take to get you there. All right, and then lastly here we have the last transition, which I think was a 3 to 2 transition. So take a look at that there. So obviously this is only information we got, so we might as well roll with this. Once again here, my final is 2, so 2 squared is 4, minus my initial 3, 3 squared is 9 in this case. So 1 divided by 4 minus 1 divided by 9 times 2.18 to the minus 18. That's going to get us an energy here, negative 3.03 times 10 to the minus 19 joules. Once again, negative because our electron is transitioning down in terms of energy. Atom going to give off that energy, negative exothermic. Let's see, we'll just go for frequency next is equal to H times the frequency. So popping in there our Planck's constant times the frequency. I don't know. Let me rearrange that there. Frequency. Set that backwards. Actually, solve for frequency would be good. All right, so let's try that again. So frequency here would be our E divided by our H in this case. And again, sending this to the other side. All right, now that we got that right numbers there, now popping our number here, 3.03 times 10 to the minus 19 joules. Again, making it positive. 6.63 times 10 to the minus 34 joules times seconds. Joules will cancel, will leave us with reciprocal seconds when it's all said and done. So we'll take that divided by 6.63 to the minus 34. Going to get us a 4.57 times 10 to the 14 reciprocal seconds. And again, you have a couple of options as well, but I'm just going to go with our C is equal to the wavelength times the frequency. Can actually solve for wavelength first this time. C divided by frequency, again dividing that to the other side, and that's going to give us 3 times 10 to the 8 meters per second divided by our 4.57 times 10 to the 14 reciprocal seconds. Again, that's going to get us to meters as the units here. So 3 to the 8 divided by our answer there, going to get us 6.57 times 10 to the minus 7 meters. We'll put it in nanometers like all the others. So 6.57 times 10 to the minus 7 meters. Again, 10 to the minus 9 meters is a nanometer. Going to get us 657 nanometers here. A little orangey red type deal in terms of the color. Any questions on any of those calculations? Definitely need to know how to do those. That's pretty much all the calculations for today's experiment as well, pretty much. All right. Also, I think it was asking which one was the longer wavelength. So obviously, I think it should be this one, as the others were in the 400s, I think. So that would be our longer wavelength here, which is what we saw when we looked at the visible part of the spectrum, right? We saw kind of the reddish being the longer wavelength, purple, violet being the shorter wavelength. Any questions on any of those calculations or how to calculate any of those things? Yeah. Yeah. That looks about what we got, I think. Yeah. All right. All right. So we've been talking about obviously this idea of sort of Bohr's model of the atom, and as we talked about, as it does work really well for hydrogen that had one electron sort of situations. But when we do move off of sort of one electron and have a lot more electrons, it really didn't sort of hold up. So later sort of experiments and ideas, and especially ideas, sort of moved us away from Bohr's model of the atom and this orbits and electrons are moving around these nice circles and stuff like that, to this idea of we really don't sort of know exactly how electrons are moving, particles like electrons are moving. And one of the first steps towards moving away from sort of Bohr's model of the atom was one done by de Broglie. And de Broglie really didn't actually do any experiments. He just sort of theorized all this. And it was later proven in sort of experiments that, he had sort of the right idea. And what de Broglie basically said was this idea that particles could have a wave-like function or character. So particles like electrons, for example, can behave like a wave. And the idea of it is sort of this idea of what's sometimes referred to as a standing wave. And when we talk about a standing wave, it's kind of like if you pluck a guitar string, right? You get the wave on the string. But because it's a guitar string, it is tied to the guitar, right? It's not going to really go anywhere, right? But it will still have this wave-like sort of function. And there will be points where there will be no amplitude, which are sometimes referred to as nodes. And obviously we'll have amplitude. So there's could be this sort of energy sort of function, and this sort of wave-like character for things like particles. And sort of the overall idea and sort of where this is sort of going is, although Bohr's idea was we had these electrons in these nice little pretty orbits sort of moving around in circles, uh, that again is sort of not going to sort of hold up. But what de Broglie sort of idea was, all right, well, we do know that we have like the nucleus, we have these electrons. So maybe they're not moving in sort of an orbital sort of path, but we do know that perhaps it has some wave-like character and it is sort of tied to the nucleus, kind of like your guitar string is tied to your guitar. Can't really go anywhere, it doesn't just fly off, right? And that's why electrons don't just fly away. They are some attraction force there to the nucleus, so it's sort of tying it there while it's moving around in this sort of wave-like characteristic. And one of the things that also came out of it is what is sometimes referred to as the de Broglie wavelength, which is what this formula is here. And this is sometimes referred to as the de Broglie wavelength. And you can calculate the de Broglie wavelength of a particle. And because things are small, the wave character of electrons is significant. So you could take Planck's constant, which is our 6.63 times 10 to the minus 34 joules times seconds, times a second. And on the bottom is our mass of the particle in kilograms and the velocity here in meters per second. So why are these units all important? Well, first off, when you look here, you do see this relationship that we talked about, that a joule is equal to a kilogram, meter squared, second squared. So again, that's what we saw earlier. And when we look at the units of just H, for example, that is joules times seconds, which means for the joules part, you can substitute in kilograms, meter squared, second squared, and that's going to be times a second. And if we take the mass in kilograms of the particle and the velocity in meters per second, what we will end up with is a second here and a second here. We'll cancel both of those out. Kilogram will cancel a kilogram, and a meter will cancel out one of the meters. And this will leave you just 1 meter left over in terms of units. And that will give you your de Broglie wavelength in meters. Now, the good news is, although the units changed, the number's still the same. So it's still 6.63 times 10 to the minus 34. And so that doesn't really change. So it's important here that you do, if you're going to calculate the de Broglie wavelength for something, that the mass, though, is in kilograms so that it properly cancels out. If you leave like the mass in grams, you'll be off by a factor of 1,000 and stuff like that. So you got to make sure that you do that. Also, the velocity does need to be in meters per second so that everything cancels out correctly. Any questions on that one there? So why don't we try one here? So calculate the wavelength of an electron traveling at 2.65 times 10 to the 6 meters per second. There's the mass of an electron you could use. See what you come up with. Okay, so let's take a look here. So again, we're going to calculate our de Broglie wavelength, which is our h divided by our mass times our velocity. Again, remember that our mass doesn't need to be in kilograms, which it was given to us here in kilograms, so that makes it easy. And also, again, our velocity does need to be in meters per second for everything to properly cancel out, which it does. Our h is still the same Planck's constant. Remembering that, again, that the joules basically swaps out in this case. If you want to see the units there, kilograms, meters squared, second squared, which is our joules part, still a second left over. So popping these guys in here, we will have our wavelength is 6.63 times 10 to the minus 34. Once again, we'll use kind of the kilogram units here instead of joules. So we can see all the units cancel. Divided by our mass, 9.11 times 10 to the minus 31 kilograms. And our velocity, 265 times 10 to the 6 meters per second. So here's again where all the units cancel. Kilograms go away. 1 second, 2 seconds. There goes both of those. And again, just one of the meters will go away. So we're left with just meters there up on top. which is good. So 6.63 to the minus 34 divided by 9.11 to the minus 31. Again, make sure you are using your exponent button. I again here would hit equals and then divide it by 2.65 to the 6th. And that's going to get us something like a 2.75 times 10 to the minus 10 meters for our electron here. So again, even a particle like an electron will have a wavelength associated with it because it does have some wave-like characteristics. Yes, sir.
I know you said that it's be provided for like default numbers like 6.63 or like 3% power. It will be, but it's just not going to be trying to say. But it's going to be.
It would be provided, so I don't know how it would be. But there may just say H, or it may say Planck's constant, it may say speed of light or C, but stuff like that. Yeah. They'll have some type of recognition of what it is, rather it's a number on a page. Yeah. Other questions? Okay. All right. So hopefully they got the same answer here. This would be good. That's what we got. Good. All right. So as we talked about here a second ago, with sort of the first major sort of idea moving away from Bohr's model, this planetary atom and electrons in these nice pretty orbits, we're again moving more towards what is sometimes referred to as the quantum mechanical sort of model of the atom, where again, we don't really believe that electrons are restricted to these nice circular orbits and orbiting the nucleus. As we're starting to see, they are particles. They have particle-like function, but they also have wave-like characteristics as well. So they're moving around in a more random sort of pattern. And one of the next sort of major sort of ideas of moving away from Bohr's model of the atom is the idea of Heisenberg and the uncertainty principle. And essentially, the Heisenberg uncertainty principle basically states that, as you know more about how, like a particle, for example, like an electron, is moving, the less you sort of know about the actual location of where it's at. And vice versa, really, the more you know about sort of its location, the less you know about how it's sort of moving and stuff like that. So there's a lot of uncertainty with that, and that's actually Heisenberg's equation there. The uncertainty of a particle's position times the uncertainty in a particle's momentum is greater than or equal to Planck's constant divided by 4 times pi. So this is the idea of like not really sure where a particle is or how it's moving or how it's getting there. And what we're really sort of moving to with the idea of Heisenberg's uncertainty principle and really what's known as Schrodinger's equations, which we'll talk about in just a second, is this idea of, although we may not sort of know exactly where a particle like an electron is at every given moment in time, how it's moving, there are sort of ways to have an idea of where we could maybe find an electron within the atom. And we're moving to more of a probability type of idea. And with that, we get into what is sometimes referred to as Schrodinger's equations, which are wave functions and stuff like that, which we obviously are not going to solve. If you ever take physical chemistry and stuff like that, you'll see the actual equations and stuff like that. I highly recommend waiting to the end of your career to take that. But it's a lot of calculus and stuff like that and derivatives. But the idea behind sort of Heisenberg and Schrodinger and his sort of equation is there is a probability of finding an electron. So instead of knowing for sure, like in sort of the idea of Bohr's model, that for sure I know an electron's in this orbit and it's traveling around in circles around the nucleus, to this idea of, we have the nucleus, not really sure exactly where the electron is at any given moment in time, not sure exactly how it's moving, but I do know that there is a high probability within the nucleus or near the nucleus, there's a pretty good probability that you're going to find an electron in that area, right? Because of opposites attract, electrons being negatively charged, protons in the nucleus being positively charged. So there should be some attraction, and there should be a pretty fairly good idea that, we can find an electron. But as we sort of move out as well, and I'll make it kind of reddish. There's usually different variants of colors. One color that kind of fades out. As you sort of move out from the nucleus, there's going to be a lower probability perhaps of finding an electron because you are further away from the nucleus, right? So it's not going to have as much attraction. So there's a lower probability of finding an electron. Does it mean you cannot find an electron far away from the nucleus? No, it just means that the probability is a little less than, if you had to pick a spot to try to find an electron, you would probably want to pick somewhere near the nucleus. That's going to be a pretty good place to probably run into an electron. And again, as you sort of fan out from the nucleus, the probability is going to decrease. So we go from this idea really of Bohr's model of the atom. You can kind of think of it like this of, for sure, I know where electrons are. They're in these nice pretty orbits going around and around. To this idea, we really don't know how electrons, which are particles, are traveling to more of the best I could do is sort of go, I think, at this area, there should be a pretty high probability of finding an electron versus say further out, there might be a lower probability of finding an electron. Now, even though there might be a really high probability of finding an electron near the nucleus, we still don't know based on Heisenberg's idea of exactly how it got there, how it's traveling. We just know, there's a good chance you might run into an electron at that point. And that's what we see here. This is a much better drawing than what I had, but this sort of darker area, and this is sort of like the nucleus, if you want to think about it here, this sort of darker bluish area is a much higher probability. And as you can see, as you sort of fan out, the bluish color gets a little bit lighter and lighter and a lower probability. It's sometimes referred to as a electron density sort of map. Now, the other major idea here that as we move away from Bohr's model to his quantum mechanical model is we no longer think of electrons being found in orbits, so no longer. And we transition to the idea that electrons can be found in what are known as orbitals or atomic orbitals. And there's basically a few different types of atomic orbitals that we come across, as you might be familiar with, s orbitals, p orbitals, d orbitals, and f orbitals. And when we think about orbitals, as we'll talk about, any individual orbital can hold a maximum of 2 electrons. So any individual atomic orbital could only hold a maximum basically of 2 electrons. Questions on that there. So again, there's the idea that's sort of spanning out of the probability map. And again, you can see this is distance from the nucleus. So closer to the nucleus, which would be back here, much higher probability of finding an electron. And again, as you fan out further, a much lower probability there, again, of finding electrons. So when we talk about orbitals, we think of orbitals really as the sort of probability maps of within an atom where you can find electrons basically hanging out. They're difficult to define precisely. They are wave functions, which is sort of what's known as Schrodinger's equations. You picture an orbital as a three-dimensional density map. Hydrogen has a 1s orbital, which is basically a sphere, and all s orbitals are essentially these sort of spheres, which are basically these circles. So I think what we're going to do is going to skip ahead a little bit to look at these orbitals, and we'll come back and talk about some other things here. So let me just find where we want to kind of skip ahead in the. All right, so we'll skip a little ahead and take a look at these orbitals here. So taking a look at these orbitals, this is the s orbital, and let's talk a little bit about s orbitals. So s orbitals, they begin on the very first energy level is where they begin. And you will have basically s orbitals on every energy level, starting with the first one. And they're called basically 1s, for example. 1s, that 1 means n equals 1. It's on the first energy level. 2s orbital, the 2s means it's on the second energy level. 3s, obviously, n is equal to 3. So on any energy level, you will find s orbitals. There's actually only one type of s orbital. So no matter what energy level you're on, there's just a single s orbital that's present. They do get larger, as you can see on the bottom picture there, as the energy levels go up to accommodate all the electrons that obviously come before them. Now, because there's only one type of s orbital, essentially any s orbital could hold a maximum of 2 electrons. So if you fill up the s orbital, you basically put 2 electrons in there if those arrows represent electrons in that line. Now, when we look at an s orbital, this is basically what it looks like. And again, it's just a sphere.
Orbital has a spherical shape with the nucleus at the center.
And again, you can think of the nucleus there, as you can see there in the center. And again, that is sort of the cloud of where electrons are randomly sort of moving around. Now, when we get to the next sort of energy level, we get to p orbitals. And p orbitals actually start on the second energy level. So they're not on the first energy level. So p orbitals start on the second energy level. There's actually 3 different types of p orbitals. There is the px orbital, which is basically this, py, and pz orbital, basically. And the x, y, and z is basically the orientation in 3-dimensional space on the x, y, and z axis, like you have a map. And they're kind of referred to sometimes as like figure eights or teardrop type of ideas, with this being the node and sort of where the nucleus would be thought of. Highest probability of finding electrons kind of in this area here for each of these. You know, kind of nucleus there. So highest probability sort of on each of these sides here. Now, when we look at this, that means that there's 3 different types of p orbitals, and each of these p orbitals, the x, y, and z, could each hold 2 electrons maximum each. And when we have a grouping of multiple orbitals on the same energy level, so in this case, there are 3 different types of p orbitals on this particular energy level and on every energy level. These are what are sometimes referred to as a subshell or a sublevel, depending on your book. And this would be what is referred to as the 2p subshell, taking into account all 3 of the different p orbitals, the px, the py, and the pz orbital. Now, because there are 3 types of p orbitals, that p subshell can hold a maximum of 6 electrons, 2, 4, and 6 electrons, basically. So maximum there of 6 electrons. So subshell or sublevel is a reference to a grouping of individual orbitals that are all the same type of orbitals on the same energy level. Speaking of that, when we talk about n equals 1, n equals 2, n equals 3, this is sometimes referred to as a shell or a level. And that is what that is sometimes referred to, like the n equals 2 shell or the n equals 2 level. Those are some terminology that is sometimes used here. So on the very first energy level, we have S's. Then we get to the second energy level, we have s orbitals, and now p orbitals start to sort of happen at that point. Any questions on that there? And here's what they look like again.
The 2px orbital is in the shape of a figure 8 along the x-axis.
And again, in the middle there is sort of where the nucleus is thought. Yeah.
There will be a maximum of 6 electrons.
No. So the s orbital, there is only going to be 2 electrons maximum, because there is only one type of s orbital on any energy level. So because there's only one type of s orbital, it can only hold 2 electrons. The p subshell is 6 total electrons, 2 in each of the 3 orbitals. And that's because they have 3 different orbitals. That is also why when we refer to sort of the s orbital, we don't really refer to it as a subshell, because there's only one orbital basically for an s, so it's just an orbital. And we only get subshells or sublevels when there are multiple orbitals of the same type, like we have with p's. And obviously our Y looks the same.
The 2p y orbital is in the shape of a figure 8 along the y-axis.
And our Z obviously on the Z. And again, each of these could hold 2 electrons.
The shape of a figure 8 along the z-axis.
And now the next type of orbitals are what are known as the d orbitals. And the d orbitals do not begin until you get to the third energy level. That is where they start. So d orbitals start on the third energy level, and still on the third energy level, you still have s orbitals, you still have p orbitals, and now joining them is the d orbitals on the third energy level. Now, much like the p orbitals, there's actually 5 different types of d orbitals, as you can see here on the bottom picture. Each of these d orbitals could hold 2 electrons, so 2, 4, 6, 8, and 10. So it could hold a maximum of 10 electrons in a d subshell. So on any energy level where there's a d subshell, all 5 of those together could hold a maximum of 10, and each individual d orbital could only hold a maximum of 2. Yeah. And as you can see, for the most part, the d orbitals look like 2 p orbitals put together, except for this guy here at the end, which kind of looks like a donut and a p orbital. But again, the same idea here, this sort of electron density map, thinking of in the center of the axis there is the nucleus. You can see that the highest probability of finding electrons are pretty much near that nucleus there. And the same idea here. Again, as you fan out, you can see less and less probability of finding electrons from that nucleus in each of these cases. Now, once again, all 5 of these guys together is going to be our D subshell, which is holding up 10 electrons. And again, here's what they look like.
X squared minus Y squared orbital has a cloverleaf shape that lies in the XY plane and is aligned along the X and Y axes.
And again,
The 3dxy orbital has a
you can see they're pretty similar.
The dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes.
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z axis.
Again, that's the only kind of d orbital. It's a little bit different than the others. Again, the others kind of look like 2 p orbitals together. But again, here in the center is where we sort of envision the nucleus. And again, you can see the highest probability of finding electrons are these things. Now, lastly here, there are f orbitals. And there are 7 different types of f orbitals, and they begin on the n equals 4 level. So again, when you hit the n equals 4 level, you still have s's, you still have p orbitals, you still have d orbitals, and now added to them are going to be our f orbitals. There are 7 different types of them, which are all these guys here. And since each one could hold 2 electrons, 7 times 2 is 14 electrons maximum if you fill the F subshell. And again, each one of these holding 2. So 2, 4, 6, 8, 10, 12, and 14 if you fill them all up. So are these shapes found in the atoms? No, again, these are sort of theoretical probability maps of where you find these sort of electrons, again, in these sort of areas within the empty space of the atom. So we have basically S's, P's, D's, and F's in terms of orbitals. And you could think of the orbitals as, or the subshells and the orbitals as sort of like rooms of where the electrons are sort of housed within the atom. Any questions on that there? Okay, so let's go back and sort of see how we get to all these things. So you might be familiar with all these orbitals and how many there are and the electrons, but we're now going to really talk about sort of the idea of with this sort of mathematical relationship and this probability of how we get to, you know, there's like 7 orbitals in this guy, or there's 5 in this guy, and all these kind of things. So I'm going to go back up to the notes and kind of fill that in. So give me a second here. We'll go back this way here. Okay, so what allows us to sort of have this idea of, you know, like I said, there's s orbitals here on this energy level and not on that energy level, and there's these many d orbitals and stuff like that, are what are known as quantum numbers. And quantum numbers, there are 4 different types of quantum numbers, and they're important in terms of, like I said, sort of the orbitals and where electrons go in the atom when we do electron configuration, and sort of how they fill the orbitals as the electrons sort of go in. So let's talk a little about the different types of quantum numbers, one of which we've already sort of talked about, which is the principal quantum number. The principal quantum number is abbreviated with an N, and it's basically the energy level for the most part. You could think of this as sort of the energy level. And as we talked about, N equals 1 is the ground state, lowest in energy, closest to the nucleus. And as we also talked about, 2 through 7 are excited states, higher in energy, further away from the nucleus. So N could have a value of 1 through 7. So those are all the possible values for N, which is the quantum number. Now, when we look at the second sort of quantum number, that is what is referred to as the angular quantum number, and that has a value of L. And L is sort of the shape of the atomic orbitals. You could think of it as it represents the type of orbital that you will find or you're talking about. So L, though, can have values of 0 to n minus 1. So those are all the possible values that you could have for L, is whatever n value that you have. You're starting at 0, taking whole numbers. It could go from 0 to n minus 1, whatever that may be. Now, like I said before, this is sort of going to tell you in most part what orbital you're talking about. Are we talking about an s orbital? Are we talking about a p orbital? Are we talking about a d orbital? Are we talking about an f orbital, and so forth? So when you calculate the value of L, that's essentially what that value will kind of tell you. You're in this orbital or that orbital, or what orbital you're talking about. The magnetic quantum number, which is m sub L, that is the orientation in 3-dimensional space. So as we saw in some of those animations, one orbital is like on the x-axis, right? One's on the y, one's on the p, right? And they're kind of moving around in that orientation in 3-dimensional space. M sub L can have a value of minus L to 0 to positive L. And these are all whole numbers as they kind of move across there. So you go from the negative value of L to the positive value of L, and you go through 0. For every single L value that you have, you could have individual M sub L values for each L value that you have. The last quantum number is the spin quantum number. And that is what is sometimes referred to as M sub S. And that really has to do with electrons. And electrons, when they are in the sort of orbital, can either be sort of arranged in the upwards direction, and that means that it has plus 1/2 for the spin. It could be in the downward direction, which means it has minus 1/2. So sometimes this is referred to as plus or minus 1/2 is the possible values that you could have for the spin quantum number. The electrons have their own spin affected by electrical fields and all that kind of stuff as well. So what we orientated is sort of if the electron goes in upward, it's positive 1/2. If it goes downward, it is negative 1/2. These are what are referred to as the 4 quantum numbers. These are the basis of all that sort of math calculations and the quantum mechanical idea. And this is the basis of when you were told, like, hey, s orbitals could hold 2 electrons, this guy could hold 6, you know, this guy could hold, 14, whatever it may be, or 10. This is the basis of how we get there. So let's talk about how we kind of get there and do some examples of what all these sort of numbers mean. So starting with, we'll come back to that. Starting with n is equal to 1. So that is the very first energy level. The possible value of L can go from 0 to n minus 1. And obviously 1 minus 1 is 0, which means the only L value you could have if you're on the first energy level is an L value of 0. And an L value of 0 represents the s orbital. And what that tells us is when we look at our guys and we hit the n equals 1 level, the only thing we have there is basically an s orbital. That is the only guy basically on that level. Now, m sub L can go from minus L to 0 to plus L. And clearly, if L is 0, the only value of m sub L we could have is 0. That basically means there is one type of s orbital. And that's, again, what we see here if we represent it with a line. Now, the m sub s can be plus or minus a half. And what that means is we could throw an electron in that way, or we could throw an electron in that way, either plus a half or minus a half, and we could fill it there. So the only possible orbital allowed based on quantum numbers on the very first energy level is an s orbital. And that's why it starts on the first one, and there's nobody else there. Any questions on that there? Now, for example, if I do n is equal to 2, which would be like our second energy level, right? If I do n is equal to 2, my L value in this case, once again, goes from 0 to n minus 1. So n minus 1 in this case is 1, which means we actually have two possible L values. We could have 0 or we could have 1 in this case. And that is basically 0 and n minus 1 is 1 in this case, right? 2 minus 1 is 1. We know that an L value is an s orbital. A value of 1 for an L represents p orbitals. So what that tells us is when we go to the second energy level, there is also going to be s's there, and there will now start to have p orbitals as we talked about. So that is what that represents. As we saw before, if we go this way with the L's equal to 0, the m sub L will equal 0 as well. And that means that we do know that on the second energy level, there is a 2s orbital present. And that 2s orbital can have a spin of plus or minus 1/2, which means just like the one below it, we could pop a couple of electrons basically into that orbital. Now, when I go to my L value of 1 in this case, which also occurs on the second energy level, my m sub L value can now be -1, which is minus L, could be 0, and can be plus 1. That is how many numbers? That is 3 numbers, yes? And each of these numbers represent a different p orbital. That's like your px, your py, and your pc orbital. So what that tells us is on the second energy level, there's also p orbitals. And there's actually 3 different types of p orbitals, which is our 2p subshell, again, our px, our py, and our pz, represented by -1, 0, and +1 for the m sub L. Each of these guys, right, can have a spin of plus or minus 1/2. Any questions on that there? All right, then you do the next one. You do n equals 3. What are all the possible L values, m sub L values you could have when you get to the third energy level? So go for it. Okay, so let's take a look, see how you're doing. So we'll start with n equals 1, n equals 3. That will then give us to our L's. And again, our L is basically 0 to n minus 1. So in this case, n is 3. So 3 minus 1 is 2. So all the acceptable values for L will be a 0, a 1, and a 2. So we're already seeing that a 0 represents the s orbital, a 1 represents the p orbital. As you could probably imagine, the 2 represents the d orbitals, basically, in this case. Now, again, for each of these L values, you could have a M sub L value. So if we have our L is equal to 0, just like we did previously, our M sub L, the only possible value it could have is also 0, which tells us, again, there's basically just one s orbital on that energy level. That guy also could have an M sub s of plus or minus 1/2. When we go to our L value of 1, just like we saw previously, our M sub L could go from, again, our M sub L goes from minus L to 0 to plus L. So that means in this case, for that guy, we could go our -1, 0, and +1, like we saw for our p orbitals, tells us there are 3 different p orbitals there on that energy level, and each of those can have a plus or minus 1/2. Now coming to our 2, our L is equal to 2. Once again, this means that our M sub L could have values of -2, -1, 0, +1, and +2. Once again, if you count up all those numbers there, that is 5, right? Which is what we know we have for our d orbitals, and why there are 5 different d orbitals in that subshell, because based on quantum numbers, you have 5 basically different d orbitals. Each of those can have basically, again, our plus or minus 1/2 in this case. Now, any questions on that there? So that means, again, as we've been seeing, our n equals 1 has our 1s orbital, our n equals 2, our 2s, and that's where we first start to see the availability of p orbitals. And that's why when we now get to our third energy level, we have our 3s, our 3p, and now we have our introduction of our 3d orbitals in this case. Any questions on that there? So, yeah.
The same thing, use like the block, like S1, T1,
Yeah, we're gonna. I think I know what you're talking about. We will talk about that in a little bit. Talking about periodic table. Yeah. Well, we relate all this to the periodic table. Yeah.
Doesn't 4S go up before 3D?
It is. We're going to talk about the order in just a second, but we're just right now talking about the different energy levels and the subshells and how we know what orbitals are on which energy level. We're going to talk about, we are leading to electron configuration, which we're going to talk about next, and sort of the order of that and why some things change and stuff like that. Yeah.
Well, the fourth energy level to be filled in order for 3D to be filled, then how do we still get those same numbers?
So we'll talk about it in just a second. Yeah, okay, and why there is that sort of difference in sort of the energy and stuff. All right, so let's talk about the fourth energy level here, and n equals 4, which will give us L values of obviously 0, 1, 2, and 3 in this case. And as we've been talking about, that is our S, that is our P, that is our D, and that is going to be basically our F. So obviously above, I did all the quantum numbers for 0, 1, and 2, so I'm not going to rewrite them. So they will all come out obviously the same as what we just did above there. So I'm just going to look at the 3 here, and that would mean L is equal to 3. That gives us M sub L values of -3, -2, -1, 0, +1, +2, and +3. Again, if you count up all these numbers, they represent individual F orbitals, and there's a grand total of 7 of them. And again, that is the reasoning behind why we have 7 different sort of F orbitals on that subshell. Each of these guys can have an M sub S of plus or minus 1/2. Now, so that gives us N is equal to 4. And again, we have a 4S, 4P, 4D. I'm going to run out of room, but imagine there are 7 lines in there, 4F there, and that is the orbitals. All right, first off, any questions on quantum numbers there and how to calculate them? We're now going to sort of tie this into some of the questions that were just asked, basically electron configuration and how the quantum numbers sort of tie into that. But this is really the basis for, why we have different orbitals on different energy levels, how many we have on there. And some of these will be some of the reasons why, how we fill them. So as we also talked about before, when we talk about a level, a subshell, and so forth. So if we had a question like the maximum number of electrons in a n equals 2 level or shell, and the maximum number of electrons in a 3D subshell, and maybe the maximum number of electrons in a we'll do a 4p orbital. So take a moment and figure out the maximum number of electrons for each of those questions. Maximum number of electrons in a n equals 2 level, maximum number of electrons in a 3D subshell, and maximum number of electrons in a 4p orbital. Okay, so if we look at it here, maximum number of electrons in the n equals 2 level, n equals 2 level is everybody on this energy level. And that means we could go 2, 4, 6, and 8 electrons, right? If we filled that guy up. Maximum number of electrons in a 3D subshell. 3D is over here. Subshell is everybody together. So that is 2, 4, 6, 8, and 10. And how about the 4p orbital is? It is actually the trick question. It is 2 electrons, right? Because any individual orbital could hold only 2, right? So we might be talking about that orbital, might be talking about that orbital or that orbital. If I said the 4p subshell, it would be 4p subshell would be 6 altogether, yeah. But any individual orbital would only be 2. Question on any of those? Yes, sir.
Tested on diamagnetic paradise.
It would be tested on what we'll talk about. So we might talk a little bit about that, but I don't know if we'll talk too much about that now. Other questions? All right, so that's what we see here when we look at our quantum numbers and our relationship to our orbitals and our M sub L numbers and our number of orbitals that are present. Now, for example, what happens if, we get to n equals 5, right? If we get to n equals 5, that would be an L value of 0, 1, 2, 3, and 4. So that's an s orbital, right? That's a p orbital. That's a d orbital. That's an f orbital. What is 4? It actually just goes alphabetical. That's like G, H, and so forth. So you just kind of go alphabetical at that point. Although when we do electron configuration, we don't go past F ever. But if you need to sort of identify what type of orbital it is, it just sort of goes alphabetical after F for the rest of them and stuff like that. Now, let's say you wanted to know, for example, how many electrons there are on a particular energy level. You don't want to like draw the lines and all that type of stuff. So if you're interested in the maximum number of electrons on an energy level, Rn, you basically could calculate it by taking 2 times n squared. So you square the n value first and then times it by 2. So we did n equals 2 a second ago. So 2 squared is 4. 4 times 2 is 8, which is the maximum number of electrons. You can do that. You get to like something like the 5th energy level, right? 5 squared is 25 times 2 is like 50. You can pop up there. So that's a quick way you can figure out the maximum number of electrons on a particular energy level without having to sort of draw all that. Any questions on that? All right, so speaking of that, we are going to tie this into electron configuration, which is sort of what we're going to talk about now. So to answer perhaps one of the questions that was asked, and we'll get to the other questions probably next time, but when we look at this sort of orbitals that we just did, and we'll just kind of draw them here. in the presence of like one electron, like in hydrogen, this is basically what the orbitals look like in terms of their energy. And what we see here is, to the best of my ability to draw in it, all of the orbitals are basically equal in energy on an energy level. So all the n equals 2 orbitals are all equal in energy. All the 3s are equal in energy. All the 4s are basically equal in energy. But what happens when you start filling an atom with electrons? And by the way, electrons do go into the atom lowest energy first, right? And then they continue to kind of fill the next lowest and the next lowest. So they kind of go fill lowest to highest in terms of when they are filling the orbitals. What happens when you start piling more than one electron is you now have a lot of electrons near each other, right? And electrons are negatively charged. So do they really want to be kind of near each other? They actually don't, right? Because they have the same charge, so they're going to repel each other. And the effect of that when you get multiple of electrons filling into an atom is there's actually a shift in the energy of these orbitals. And what happens is when you start filling it in with multiple sort of electrons, you get this sort of difference in energy level, not drawn to scale here, but we'll do our best. Like 2s, and then you got like your 2p, then you got your 3s. Then you got your kind of 3p. And right around here is where there's a major switch that occurs, is actually the 4s and the 3d. They kind of switch in terms of energy. And it's actually the 4s that actually becomes lower in energy, and then the 3d is higher in energy. And that's going to affect, obviously, the way the electrons go in. They're going to come here first, here, they'll come here next, they'll come here, they'll come to the 3p. And at that point, they actually will fill the s first and then the d. And that pattern follows all the way up. The s's always get the electrons first, and then they go to the d. So there is this sort of difference in order of how the electrons go into the atom. And that's important for electron configuration. And when you have multiple electrons, you get this sort of shift in energy of these guys. Now, there is a pattern and order at which the electrons go into the atom, and it is something that you actually can sort of create for yourself to help you remember how to write electron configuration. And the best way to do it really is to think about what we just talked about, which is on the very first energy level, that is where S's start. It is not till the second energy level that we have P. So you just go a little bit to the right and underneath, and you write 2P. Not to the third energy level that D's start. Go a little bit to the right and below and put the D's. Not to the fourth energy level that F start, a little bit to the right there and F's. At this point, you basically could just fill in the numbers like 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3D, 4D, 5D, 6D, and 5F. And this is basically the order at which electrons go into the atom. And as you can see there, it took me all of like 10 seconds basically to do it. You always start up here and you basically follow this arrow, this sort of zigzag thing. And this will give you the correct order. And as you can see here, 3P goes through the 4S first to the 3D, and you basically can just continue that pattern and zigzag back and forth. As you can see, again, 5S before R, 4D, 6S before, and all that kind of stuff. And this will give you basically the order for electron configuration. If you know how to do that, and you know what we talked about, that the maximum electrons for an S is 2, a P subshell is 6, a D subshell is 10, and an F subshell is 14 electrons, you basically could write any electron configuration that you would need to do. And again, that is something that's pretty easily created by just remembering the 1, 2, 3, and 4, and you can fill the numbers below it. Even if you can't remember where to stop with the numbers, and you go too far on all of them, you will still probably be okay, because you'll never probably get down there in most cases. And if you put an extra like 7D, which there's not, or a 6F, which there's not, you'll be okay in most cases anyways. And most of the things that you write electron configuration for. So that is where we're going. And since we're out of time, we will do it tomorrow and do some examples.